Welcome to a deep dive into the revolutionary slip layer physics behind the AEON CASIMIR Initiative. In this chapter, we explore how advanced propulsion systems overcome the limitations of traditional flight by decoupling the craft from its environment. The slip layer is not just a technological upgrade, it's a fundamental shift in how vehicles interact with air and space. By creating a seamless boundary, the slip layer allows for smooth transitions between atmospheric and vacuum conditions, eliminating destructive forces like shock waves and radiative drag. Let's begin by understanding why this innovation is essential for high-velocity travel. Propulsion without proper environmental decoupling leads to severe challenges at high speeds. As a craft accelerates, it faces atmospheric shear, shock formation, plasma heating, and radiative drag. These forces can damage or even destroy the vehicle. The slip layer addresses this by acting as a protective envelope, ensuring the craft can move effortlessly from dense atmosphere to the vacuum of space. This innovation is crucial for maintaining structural integrity and operational safety during extreme maneuvers. Like a physical coating, the slip layer is a thin region where spacetime itself transitions smoothly between the external environment and the engineered interior of the craft. This is achieved through a controlled metric, blending the outside and inside spacetime properties. The result is a continuous, stress-free interface that eliminates abrupt changes in curvature and energy, making high-speed travel safer and more efficient. The interface between the hull and the environment, the slip layer enforces a unique condition. The total stress energy must approach zero. This means that pressure spikes, shear gradients, and thermal discontinuities are all smoothed out. The craft experiences a gentle, continuous interaction with its surroundings, rather than abrupt and damaging forces. This smoothing is essential for maintaining the craft's integrity at high speeds. Traditional shock waves are caused by sudden compression of air in front of a fast-moving object. With the slip layer, incoming paths, called geodesics, are gently refracted instead of being compressed. The transition from air to vacuum is spread across the slip layer, so the local Mach number near the hull drops to zero, even if the craft is moving much faster than the speed of sound. This means no sonic booms or destructive shock waves form. Aerodynamic heating is a major challenge at high speeds, as friction and pressure can cause extreme temperatures. The slip layer removes these sources of heat by eliminating shear stress and stagnation pressure. Instead of heating the hull, thermal energy is phase-shifted into electromagnetic fields, absorbed by plasma rings, or redistributed into the vacuum. This keeps the craft cool, even at hypersonic velocities. Slip layer's effectiveness is enhanced by Casimir boundary engineering. This technique creates a gradient in the vacuum's refractive index around the craft, bending particle paths and field lines smoothly. It's similar to how water flows around a smooth stone, but here, spacetime itself is being shaped. This approach allows the craft to glide through both air and vacuum without resistance. Plasma rings play a vital role in stabilizing the slip layer. They enforce phase coherence, dampen boundary oscillations, and prevent the vacuum from losing its engineered properties. By acting as a dynamic buffer, plasma rings absorb disturbances before they can affect the slip layer, ensuring smooth and stable flight even in turbulent conditions. Electromagnetic fields are used to actively control the slip layer's thickness and strength in real time. This allows the craft to adapt instantly to changing conditions, such as atmospheric entry or turbulence. The result is a seamless transition between different environments, with the slip layer always optimized for current flight conditions. One remarkable benefit of the slip layer is its ability to reduce the craft's RF, infrared, and radar signatures. Unlike traditional stealth coatings, the slip layer achieves this by causing electromagnetic waves to cancel each other out, redistributing thermal radiation, and allowing plasma to absorb and re-emit energy coherently. This makes the craft less detectable as a natural byproduct of its advanced physics. Slip layer's thickness can be adjusted depending on the environment. During atmospheric flight, it may be several centimeters to meters thick for maximum protection. In near vacuum, it shrinks to a minimal envelope, and in deep space, it's maintained only for shielding against radiation and micrometeoroids. This tunability ensures optimal performance in any condition. Slip layer's thickness is inversely related to the gradient of the engineered metric. In regions where the metric changes rapidly, the slip layer becomes thinner, and where changes are gradual, it thickens. This dynamic scaling allows the craft to maintain a stable and effective boundary, regardless of external conditions. If the AEON CASIMIR systems are powered down, the slip layer vanishes, and the craft immediately returns to classical aerodynamics. This means it experiences normal drag, heating, and airflow, just like any conventional vehicle. Importantly, there are no lingering effects on spacetime, ensuring safe and predictable operation at all times. The slip layer system is designed to fail softly. If coherence is lost, shock formation and thermal loads return gradually, not suddenly. There is no catastrophic collapse of the boundary, which means the craft remains safe and controllable even in the event of a malfunction. This fail-soft approach is a key safety feature of the AEON CASIMIR design. The slip layer is deeply integrated with the AEON CASIMIR propulsion stack. It relies on plasma control and boundary engineering to function, and in turn, it enables silent atmospheric flight, hypersonic survivability, seamless space transitions, and long-term structural health. Without the slip layer, the advanced propulsion system would be destructive and unsustainable. Chapter 6 reframes environmental interaction as a spacetime problem, not just a matter of fluid dynamics. Shock, drag, and heating are seen as symptoms of discontinuities in the spacetime metric. By resolving these discontinuities, the slip layer unifies atmospheric and vacuum flight under a single, coherent framework. With the slip layer, the craft no longer battles the air or vacuum. Instead, the medium never fully touches the craft, allowing for frictionless, shock-free, and heat-free travel. This principle marks a fundamental shift in how we approach high-speed and spaceflight engineering. AEON LCV Ω1, a domed lenticular vacuum-metric vehicle, serves as the primary testbed for these advanced slip layer technologies. Operating in northwest Indiana, this craft demonstrates the real-world application of metric boundary engineering, plasma stabilization, and electromagnetic phase control. Its performance validates the theoretical foundations discussed in this chapter. Slip layer manages multiple forms of stress energy at the hull interface, including matter, electromagnetic, plasma, and Casimir contributions. By balancing these components, the slip layer ensures that the total stress energy remains smooth and continuous, preventing destructive forces from reaching the craft's structure. Phase coherence, enforced by plasma rings, is crucial for the slip layer's stability. It ensures that oscillations and disturbances are damped before they can disrupt the metric boundary. This coherence is maintained dynamically, adapting to changes in flight conditions and environmental factors. The slip layer's electromagnetic controls allow it to respond instantly to turbulence and other environmental changes. By adjusting its thickness and strength, the system maintains optimal protection and performance, ensuring smooth flight even in unpredictable conditions. During atmospheric entry, the slip layer adjusts in real time to changing pressures and temperatures. This seamless adaptation prevents the formation of shock waves and excessive heating, allowing the craft to enter or exit planetary atmospheres without risk. One of the most impressive outcomes of slip layer technology is silent flight. By eliminating shock waves and minimizing aerodynamic noise, the craft can travel at high speeds without producing the loud booms or roars typical of supersonic vehicles. This opens new possibilities for stealth and civilian applications. The slip layer enables the craft to survive and operate efficiently at hypersonic speeds. By suppressing drag and thermal loads, it prevents the structural and material failures that typically limit high-speed flight. This capability is essential for next-generation aerospace vehicles. Transitioning from atmosphere to vacuum is a major challenge for conventional vehicles. The slip layer allows for a seamless transition, maintaining optimal protection and performance throughout. This makes the AEON CASIMIR craft uniquely capable of both atmospheric and space operations. By eliminating destructive forces like shock, drag, and heating, the slip layer greatly extends the structural lifespan of the craft. Components experience less wear and tear, reducing maintenance needs and increasing mission reliability. Key safety feature of the slip layer is that it leaves no lasting changes in spacetime. When the system is powered down, the environment returns to normal instantly. This ensures that the technology is safe for repeated use and does not alter the surrounding environment. If the slip layer loses coherence, the return of shock and thermal loads is gradual and predictable. This allows for safe emergency procedures and prevents catastrophic failures, making the system robust and reliable even under stress. The slip layer's effectiveness depends on the synergy between plasma rings and electromagnetic fields. Plasma provides dynamic buffering and coherence, while EM fields allow for precise control and adaptation. Together, they create a stable and tunable protective envelope. Thermal energy that would otherwise heat the hull is redistributed into vacuum mode adjustments. This means the energy is absorbed and managed within the engineered spacetime, further protecting the craft from overheating and structural stress. The slip layer causes electromagnetic waves, such as radar and infrared, to cancel each other out through phase manipulation. This reduces the craft's detectability and enhances its stealth characteristics, all without relying on traditional coatings. Plasma rings not only stabilize the slip layer, but also absorb and re-emit electromagnetic energy coherently. This process further reduces the craft's observable emissions, making it less visible to sensors and detection systems. In the vacuum of space, the slip layer is maintained only as a thin envelope for protection against radiation and micrometeoroids. This efficient use of resources ensures the craft remains lightweight and agile while still being protected. The slip layer's core function is to interpolate smoothly between the external and internal spacetime metrics. This mathematical blending eliminates discontinuities, ensuring that the craft's boundary is always smooth and continuous, regardless of speed or environment. Even in the event of a slip layer failure, the system is designed to avoid catastrophic collapse. Instead, protective effects diminish gradually, giving pilots and systems time to respond and recover. This design philosophy prioritizes safety and mission success. The slip layer unifies the physics of atmospheric and vacuum flight. By addressing the root cause, metric discontinuity, it provides a single solution for all environments. This unified approach simplifies design and operation, paving the way for future aerospace advancements. With the slip layer in place, the craft avoids all classical aerodynamic penalties. There's no drag, no shock, and no excessive heating. This allows for unprecedented speed, efficiency, and safety in both atmospheric and space environments. The slip layer's properties are controlled in real time by advanced onboard systems. Sensors and processors constantly monitor conditions and adjust the slip layer's parameters for optimal performance. This automation ensures the craft is always protected and operating at peak efficiency. By minimizing both acoustic and electromagnetic signatures, the slip layer enables silent and stealthy operations. This is valuable for both military and civilian applications, where discretion and low detectability are crucial. Unlike traditional stealth technologies that rely on special coatings, the slip layer achieves signature reduction through fundamental physics. This makes it more robust, less maintenance-intensive, and effective across a wider range of conditions. Plasma rings act as a dynamic buffer, absorbing and neutralizing disturbances before they can affect the slip layer. This buffering is essential for maintaining stability and performance during rapid maneuvers or in turbulent environments. Traditional flight problems like shock, drag, and heating are all symptoms of metric discontinuity at the craft's boundary. The slip layer solves these by ensuring a smooth, continuous transition between the craft and its environment, fundamentally changing how vehicles move through air and space. Slip layer technology represents a new frontier in aerospace engineering. By addressing the fundamental physics of environmental interaction, it opens the door to faster, safer, and more efficient vehicles. The principles outlined in this chapter will shape the next generation of flight. To summarize, the slip layer enables seamless, shock-free, and heat-free flight by engineering the boundary between the craft and its environment at the level of spacetime itself. It integrates plasma, electromagnetic, and Casimir effects to create a tunable, robust, and safe protective envelope. This chapter establishes the slip layer as the cornerstone of AEON CASIMIR propulsion. With Chapter 6 complete, the AEON CASIMIR Initiative stands at the cutting edge of propulsion physics. The slip layer's principles will continue to inform future research and development, driving innovation in both military and civilian aerospace sectors. The journey toward truly seamless flight has only just begun.